Alright, time for another DraftPhysics.com, debatephysics.com also. Video presentation. Unfortunately, debate is always in this broken form where I go to extensive trouble to explain how something works and, what the arguments are about and what the details are and all that kind of crap, and you just get these little trite, mushy sentences from the opposition claiming something else to be the truth, and it's not the truth, and it's not a fact, and it's not any of that stuff. And so a pyrrho comment. So I did already make this video a whole hour's worth, and went through so many subjects. It's just unfortunate that my Linux disappointed me. Somehow the microphone had gotten maladjusted and was not performing correctly, and so it's all gibberish now, and it's just really irritating. So I'm going to read this pyrrho comment and respond to it by explaining, all of these variables that none of these people want to account for, they don't want to pay attention to, and it's really kind of irritating. So let's start with how to measure energy. So we'll start with Pyrrho's first sentence here. Whoa, can't hit anything here. That's really annoying. That keeps happening. Anyway, you click anywhere on the damn page and it's a link to something. The only experiment needed is to launch the two different masses from a spring and see their velocities. Okay, so let's first understand the limitations. So everything, we always talking about these things in ideal context, and it's really hard to get to create the ideal spring, for example. So something as simple as a tennis ball thrown against a wall. I always thought that, it comes back pretty good, 90% or some kind of, it's 75%, 25% lost energy, 25% of the energy disappears, in the lack of conservational function of the spring of the ball. And so who knows what the real numbers are for springs, and who knows in what form of spring those numbers get higher or lower, a stiff spring versus a loose spring. And what we know about springs is you're going to push something with a spring. One of the liabilities is that the spring is compressing, it's building up pressure, and as it expands, it's losing pressure. And the very opposite thing's happening to the object you're pushing. So as you're pushing it, its velocity is increasing. As the spring is pushing, its velocity is decreasing, its pressure. So obviously that's not very good. It's not conducive to the idea that all the energy is going to get in, because as the spring is losing velocity, the object has gained velocity, and there's going to be some point where the spring is just going to be pushing air, and it's going to do this oscillating thing. And you can see that in springs, and they're bouncing over here, and they're bouncing over here, and they're doing all this bouncing around. So obviously all the energy, all the momentum didn't get into the object, because the spring is sitting there wobbling, telling you, I still have energy, ha 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 ha. So we know we don't have a 100%, And what percentage we have is going to be built out of understanding whether the spring is in a confinement, is it a plunger? Are you actually pushing something with a spring? Are you pushing it with an object that you're throwing at the object, right? So you have to have good contact with the spring, and to be able to push it. You don't want to be hitting it, because if you hit it, you give it a high velocity, the spring loses some of its pressure, because the distance it moves, it loses pressure. It's not pushing anything while it's doing that, because it already pushed it. And then it might hit it again and give it a little boost and hit it again. So we know that's not very efficient. So there's lots of places where you can lose a lot of the energy. So none of this is as precise as you want it to be. And again, I'll say it again, the whole reason why Joule is famous is because he had to contrive, he wanted to do something precise. And so he had to go to all this trouble, to make an isolated room, no vibrations, no heat, no anything, make insulated tanks, of water, make very precise thermometers, the most precise thermometers ever made, all of this kind of crap. And then the big flaw, though, is that he didn't just tie his propeller, to an object moving. He didn't just launch something, have a loose string, and then have the string tighten and then pull the thing and then spin the thing and then see how much energy it had. Unfortunately, he did this, ignorant of the gravitational function, and he dropped things in gravity. And he didn't drop them. Obviously, you can't. When you have a string tied to them and you're stopping them from moving, what you're really doing is slowing down how fast they're falling in the gravity, and you're increasing the amount of time, they're going to be able to collect energy from the gravity. So it's like the difference between dropping something a certain height and then dropping it in increments. If I drop it in increments, I'll double the amount of time. I can triple it, by making these stairs even smaller. And the fact is, I can increase the amount of energy I'm going to get from the falling process by not allowing the object to accrue a velocity. So if I can retard how much velocity it collects, I can keep it in the gravitational pressure longer. So it's the same argument as lifting a weight. You know, I know, physics doesn't know, but we both know it's more work to lift a heavy weight slowly than to lift it quickly. You'll use more calories. You'll expend more energy. Just a fact. The same is true for dropping it. Letting go of it's really easy. Dropping it slowly is a lot of work. So obviously this is true, and so you're doubling you're extending the amount of time the object is collecting gravity. That means that it's actually collecting more force. And so you have more force to move something with this falling. And so you can slow down how fast something falls and increase the total amount of energy you can get out of the falling process. You can take advantage of the fact that you can, just as you can take advantage of launching thing at a high velocity to a certain location. You want to get to a certain height, 2 miles. All right. If you go 60 miles an hour, you'll use 1,000,000 times more fuel than if you launch it as quickly as possible, thousands of miles an hour. Then you'll be in the gravity, say, let's just say in a spaceship example, you'll be in the gravity 87 seconds. You go slowly, you could be in the gravity for 8.7 minutes. All right, a huge difference. And the fact is the longer you're in the gravity fighting it, the more energy you're going to have to expend to get there. And the faster you can get through the gravity, the less gravity you'll have to fight, because it's a time-dependent force. And I'd say that's such an obvious statement. I don't know how anybody can disagree and be rational, frankly. I don't know how a rational person can't understand that gravity is about time. It's about how much time, like sunlight, how much time you're exposed to it. And if I run through the sun very quickly, not too much sun hits me from house to house. And if I do it slowly, lots of sun hits me. And the same thing happens, when you shoot past a gravitational field. The faster you move across the field, the less the gravity is going to bend your trajectory. The slower you go through the field, the more it's going to bend you, the more likely it is you crash. I mean, these are just such basic facts. Clearly, time-dependent force. Time is what controls the force. Exposure. The amount of time you're exposed to the current of the stream. The amount of time you're in the wind. I mean, it works the same way as all these other things. And I just don't know how anybody rational can't acknowledge that appears from every piece of experimental evidence to be true, that's exactly how gravity works. If I'm coming into the Earth and I apply a force, all right, so I have a 500 mile an hour velocity when I reach point A. I'm moving 500 miles an hour, and I have another object, same mass, and I just let it fall. Okay, this one's going to take, let's say, 10 seconds. This one's going to take 1/2 of a second in the gravity. This one's only going to have a half second work. It's going to hit the ground at 504.9 miles per hour. Okay, it's going to gain almost nothing from the gravity. This one is going to hit the ground at 100, and it's going to be all. Okay, the fact is it's going to collect that gravity in these time units, and all of its momentum, all of its velocity is going to be derived from gravity. Almost none of this thing's velocity is going to be derived from gravity. So a meteor coming into the Earth, it doesn't matter. The Earth's gravity isn't helping the meteor at all. The meteor has so much more velocity than it's not going to be in. It's going to be in the gravity for 1 second. Insignificant gravity. It's going to be in significant gravity so little amount of time that it's not going to have any effect at all on its velocity or how much energy it's going to hit with. It's not going to make any difference. The substance of its energy is in its velocity coming in. And because it's going to be in the gravity so little, it's not going to add much at all to its velocity. Tiny percentage of its total energy will be from the Earth's gravity. 99.9% of its total energy will be what it brought coming towards the Earth. And that proves that the time formula works. mgt works whether I give it a velocity ahead of time or I don't. mgh fails. It can't answer the question if I give it a velocity. It can only answer one stupid question. How far did it fall in free fall? And that's it. And then let's understand the H part fails if you don't recognize that if I allow it to fall down a staircase, it's more time in the gravity and it's more energy. It gets that answer wrong. It thinks these two things are equal. 2 seconds of gravity is the same as 4 seconds of gravity. That's just not true, okay? And that's the experiment they haven't done. So in 300 years of debating these subjects, they've never done any of these experiments, all right? They haven't done any of them clinically, carefully, any of that stuff. And a simple experiment as 4 pounds. This was argued 300 years ago to kings, to the mistresses of kings anyway. 300 years ago they argued this stuff, and they still haven't proven any of it. They just claim it. So Leibniz claimed that 4 pounds dropped 1 foot is the same as 1 pound dropped 4 feet. Okay, this is in the gravity for 1 second, let's say. This is in the gravity for 2 seconds. Okay, not 4. And it's just, I think, obviously clear that these two things can't equal each other. Okay, now if you took the 1 and dropped it down a staircase, then you can create the same energy, because you can double the amount of time it will fall. Free fall, free fall, free fall, free fall. You'll get 4 units of time, so you'll have 4 seconds. Then it's the same thing. So if you use a pulley or some other device to change how long it takes for the object to fall, then you can make this equal that. But in pure free fall, no chance. All right, that's a first little bit. Let's see how we can go with the next sentence. I gotta figure out some way how to move these things without my... I'm using a rechargeable mouse, and it's really nice that it recharges, but it really sucks that it turns off all the time to save battery life, and then you have to click something, and every time you touch it, you're in trouble. But anyway, I'm trying to click things. The only experiment needed is to launch 2 different masses from a spring and see their velocity. So my simple argument is that obviously that doesn't work. Our joule would have done it. It's not that simple. If it was that simple, then that would be all you'd have to do. And my argument is much better if you can collect the energy. So if you can force the energy into a box, if you can shove something, a moving thing, into a box and it gets trapped in the box, and then you measure how much the box moves, like a ballistic pendulum, or you do some other method to attempt to collect the linear velocity as completely as possible, that's much better than attempting to see if your launching device, which is it's a constant, the deceleration is going to be constant. You're measuring the velocity where. So this happened in a lot of these rickety, cheap experiments people do, where you really do have to pay attention to all these little details. So the fact is, if I wanted to compare the velocity of 2 objects, pyrrho, you can just sort of understand that this one with 1 velocity is only going to travel this distance. This one with twice the velocity is going to travel this distance. And what is known is that this is going to be 2 units of time. 1 unit of time here, 1 unit of time here. this is going to be exactly the same as this 1 unit of time. This experiment, one velocity will reach here, 1v here. So that is 1/2 the speed will be at 3/4 of the distance down the track. That's a fact. So this friction is less than this friction, kind of obviously. But so what's going to happen? So if I let these objects roll a distance, right, we know this thing's doing the same thing. The 1-3 kind of thing is happening to it too. But I mean, the point is that obviously this thing, okay, the smaller distance, it's losing all of its velocity. It goes from its peak to 0 in this short amount of distance. So obviously when you're measuring, there's a huge liability because these two scales are so different. And so you have to measure over this, you can't measure over the same distance. So if I use 5 inches as the distance I'm going to measure, at 5 inches I'll measure their velocity. Well, obviously in 5 inches this one has lost 90% of its velocity, and this one's only lost 5%. So that wouldn't be a very fair comparison. So obviously how you measure this instantaneous velocity when the velocities are constantly changing, it's a real issue. Okay, so it's not as simple as just saying, oh yeah, we'll just take an average where, in what time, and then if you let something hit, the real liability here is that you can crash something into something, but the idea is you have to crash it really quickly into whatever you're going to use as your measuring device. The longer this distance is, the huge disadvantage for the slower object. The slower object has a huge disadvantage because it's going to be losing so much of its energy. And this goes to pendulums and their arc. Clearly, the more you go this way, okay, the harsher the gravitational force gets. And the tiny amount of distance out here is the same energy as a big distance here in the flat part. So this flat part, this much distance equals the same energy as, a tiny little dot of energy here, distance. So the distance here has so much more energy than the distance here. These are all important details, and you don't care about any of them, and they're all really important, and blah, 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 blah. So it's not as simple as. This is, and look, and you've let the guy who was supposed to do the we've been over this experiment so many times, but, do you really believe? So here we're talking about springs efficiency. Look how inefficient this is. It runs out of, look how fast it runs out of energy. And it's the Newton's cradle, and all I got is little strings to be a problem, a little bit of atmosphere, and, it runs out of energy fairly quickly. They seem like pretty hard steel, but it matters how hard they are. And they'll lose energy because they actually do physically dent. Just a fact. All right, so this experiment where, I have a thing, I put it in, I get, 100 in, 100 out, 100 in, 100 out. And obviously look how much I'm losing. So like the tennis ball, it's 25% of the energy. I throw a tennis ball at a brick wall, I only get 75% of the energy back. I mean, it seems like more than that, but it isn't. Huge losses. So measuring your energy in a system that's losing energy so dramatically isn't too ideal. But here's the experiment. I mean, he was supposed to do it. Physicist Michael, you're going to let him off the hook. You mention him here. And this is the kind of shenanigans and bullshit. So he bought the materials to make a big one of these. Okay, with nice distances, the whole thing, make it measurable. Do it to a scale where you can measure it. But this is your theory. All right, so 1 in, 1 out. And if I glue these 3 together, your theory says that this goes in with 100, 150 goes flying this way, 50 goes flying this way. So now I have 200. I had 100 momentums of motion in the universe. Now I have 200 units of motion. And when they come back together, somehow only 100 pops back out. That's your wacky theory. That somehow I have a car crash with a car that has 150 momentum and one that has 50 momentum. They crash into each other, and somehow I can make the energy disappear. When no, the truth is there's only 3 choices, right? They hit each other and they crush, okay, and I get 200 momentums worth of crushing. Or they hit each other and make a ton of heat, okay, I get 200 momentums worth of heat. or they hit each other and they bounce, and I get 200 momentums worth of bounce. I don't get just 100. So again, just bullshit. Illogical, inconsistent, and the fact is they haven't done any of these experiments. All of these experiments go over and over. All of these experiments, simple experiment. I put a mouse on the scale. It bends the scale a certain amount. Now the mouse has little roller skates on. I turn the scale sideways and I release it, and the mouse rolls off at a speed. I say it's 1 mile an hour. I do the same thing with an elephant. Put him on the scale, tip the scale. Elephant on roller skates. Let go of the scale. The elephant rolls away 1 mile an hour. Okay? You know, just simple experiments, and you haven't verified any of this. You know, this is telling you how much momentum gravity is actually giving you when you're standing on the earth. When you're sitting here on the earth, you have momentum and you're transferring it into the ground. At every second, you're transferring the energy into the ground. You're causing pressure onto the earth, and the earth is pushing you back up. And it's just a fact that that's what you're doing. You're pushing in, it pushes you back. You push in, it pushes you back. And we can't see that oscillation, but that oscillation's clearly happening. Brother. Anyway, this is the same as when physicist Michael and I think others launched different masses using the same spring. So launched them how and in what form? So I could argue that Brozo, okay, probably had the best idea in terms of how to do this experiment. And that is, you take a sheet of glass, all right, and you take a round object, so you have very little friction point, all right, and you skid, okay, the object across the surface. Now you could put some oil on it, make it even better. You could wax it, do whatever you can to maximize how little friction there is. Little ability for this surface to impose, okay, its irregularities, bumps, and sandpaperness. Take away all the sandpaperness. Make it as smooth and silky as possible. You could even talk about even putting fabric down, you know, and having static electricity and blah, 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 and how that might even make it move very freely without doing air tracks and other kinds of nonsense. And when he did the billiard ball experiment with a simple lever, okay, and a spring, he got quite consistent results. That is, the one mass and the half mass twice the distance. He got twice the velocity, okay, in the half mass. So blah, 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 blah. I can point to that experiment, which is pretty decisive, but whatever. And pointing out that there's twice the energy, okay, there's only twice the momentum. There's only the same momentum, and there is no extra energy in the lighter object going twice as fast. It didn't take extra energy to create it. Okay, it took the same amount of energy to make a half mass go twice the speed as it is to make a full mass go half the speed. Same thing. All right, so now let's talk about the other dopey experiments, though. One of them's the Brozo, again, okay, with metal hard drive disks as wheels. So this is his monster truck kind of version. And then we have the physicist Michael standard buy it from the physics company you know, cart, okay, that has whatever 10 metal wheels, okay, and that's supposed to be low friction, right? A bunch of wheels supposed to be low friction. No, I think what it's designed to do is hide the momentum. So the real argument is that this is a real problem in your experiment. Wheels, okay, wheels are a real problem because they can store a lot of energy if they're heavy. So if your wheels are heavy by comparison to your total mass, then they can be storing momentum that you won't see as linear momentum. So it's actual momentum you have, it's stored, so it's real momentum, it's just not linear, it's not in your direction yet. And when you hit the surface is when it'll be turned into pressure. So all of a sudden you have your real linear momentum, but then you have some extra MV, all right, in the form of the angular rotation that will be consumed, and now you'll push a little further because you have the stored MV. So the wheels, flywheels, is essentially what wheels are, is flywheels. Having flywheels on your cart means you've stored energy, and the cart contains more energy than the linear motion would indicate. So that's got to be accounted for. So we saw nothing. Physicist Michael conceded my argument. I mean, I made the argument to him, well, this cart's got a bunch of metal wheels. You know, how much momentum is trapped in your cart wheels? And he says, I don't know, I'll ask the manufacturer, blah, 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 but we never got an answer. And clearly in the Brozo case, we know metal hard disks have quite a bit of momentum because you pick up a hard drive when it's on and you can feel, okay, how much power those spinning disks have. So they're obviously a significant enough mass. So those are real flaws, right? These are real things to avoid. So you want a mechanism, you know, that doesn't have these kinds of defects in it. All right. Now I've pointed out that air tracks are also a huge liability, in the sense that, you know, just a fact that the air track is another source of energy. So like the flywheel of wheels, the air track is pumping air, okay, that has momentum. And the fact is that the little cart that sits on top of the track, all right, all it has to do is tilt a little bit this way. You know, this end tilts up a little bit, this end tilts down a little bit, then all of a sudden it has an exhaust. It has a little jet engine. So it's a real problem. If the two carts hit each other and they pop up, that is, they pop this way, right, because they hit each other, you can understand that both of them would be creating this exhaust, okay, and they'd both have more momentum than they actually had, because you're providing a source of energy, an exhaust, because the carts are sitting on the track and oscillating. So I found that I made a round pipe air track, and I found the same problem in that the PVC pipe, you could get to stay in one position, but it would be constantly oscillating, okay, in that position. And you could sort of understand that all it has to do is gain motion with a little bit of a direction, a little tilt in the motion, and obviously it would be ejecting more air out one side than it would be ejecting out the other side. And obviously that would be increasing its linear momentum. It could appear to have a lot more linear momentum, because once it was going, it would keep going because of that exhaust. So lots of liabilities, lots of variables to be considered. These aren't perfect experiments. The whole reason, again, why Joule was famous is because he went to the trouble to create a very elaborate experiment that had, again though, the simple flaw was that he didn't bang. He didn't use his device to collect energy in linear motion, and instead he used gravitational energy. Okay, and you can't, if you think gravity is 4 times the distance is 4 times the energy, then obviously your outcome is going to be wrong. Okay, it's going to be an exaggerated number, because you're not appreciating that things falling at different speeds are collecting different amounts of gravitational energy. Yeah, I think I went over that, but okay. See, I can't remember what parts I've already talked about in the previous video, unfortunately. Alright, so, you know, Pyrrho's responding to a video that was on a very specific subject, and of course he's not being very responsive to the outcomes of that very specific video about a very specific subject. So I have a circumstance. I can take a car, okay, I take a mass, a 5 mass, and I can plow it into an unyielding wall, okay, and I can allow the mass to show me how much crushing it gets. So it gets a certain amount of crushing happens to the mass, okay, it dents a certain amount. All right, and then we can call that a unit of energy. You know, 1 unit of energy is this much compression on a 5 mass. So let's make a 5 mass out of clay or something, and it smishes of this certain amount. All right, and the theory is that, well, if I take 2 of those, okay, and crash them into each other, that what will happen isn't like I'll get more energy. I'm just going to get, this one's going to say this one looks like a brick wall. It's not going to do anything extra except consume the pressure over 2 crushable surfaces. So this one will crush 50 miles an hour's worth. This one will crush 50 miles an hour's worth, you know, if it was 50 miles an hour, as an example. All right, so I'm going to get the same outcome. There's not going to be 4 times the energy in this crush. So the Mythbusters essentially did do these experiments, and that's how it comes out. This crushes, and this crushes the same amount. The whole point of their experiment was just to prove that this crushes the same amount if I bang it against another one that weighs the same momentum, as if it was a brick wall. So this object crushes exactly the same whether it hits another moving object, as long as they have the same energy. So again, it has to be the same mass object moving the same speed. If it's something else, then it'll crush more. But if they're the same, it's like this just crashed into a brick wall. So it's just like all these two things are seeing is the brick wall between them. But if I put the crushable in between them, okay, then what's going to happen is yes, the half that was here and the half that's here is going to be a hole here. And so it's going to be exactly the same amount of crushing. It's just that it's all going to be in this one object. The one object will crush this portion and this portion. All right. So it's only going to have two portions of crush. It's going to have one and here, and if I did it a second time, I'd have one. It's just two. There's no 4 anywhere. There's not 4 times the energy here than there was if you took 2 of these. So if I let the 2 hit and let them crush, same difference as just putting the one object in between them. So if you're standing between 2 cars hitting you, moving 50 miles an hour, the crash will feel like 100 miles an hour to you. But it won't be 4 times worse. It'll only be twice as bad as just one car hitting you. It's only twice as bad, not 4 times as bad. So again, he ignored the whole video. And it's just pretending that, well, we'll push it with a spring and therefore we can know exactly how much energy it has. Not exactly. I'm not saying that won't work. I'm just saying it has to be accepted that the spring isn't ideal. That like the tennis ball, 25% of a loss of energy is huge, and you have to account for that. You can't just pretend it isn't a problem, just like you can't pretend heavy wheels aren't a problem. Oh, damn this fucking... See if the microphone's still working. Yes, thankfully. Okay. I am recording, right? yeah, okay. Hopefully this is a video. Alright, click on this instead. Alright, physicist Michael and I think others launched different masses using the same spring. And yeah, what was the form of the spring in the physics Michael example? We have plastic carts with metal wheels. The spring is a plastic plunger compressing a spring. So the plunger itself now is also going to consume momentum. And it's also not a guarantee that the spring and the plunger are making perfect contact. So there also could be hitting instead of pushing, which are also different concepts. Hitting something is different than pushing something. Throwing a hammer at you and holding the hammer and hitting you are going to end up being different events. But anyway, that's just an analogy. One I've dreamed about, actually. Anyway, different masses using the same spring. The spring, when compressed, surely contains a set amount of energy to release. Yeah, that's the problem, though. It can't release all of the energy because it's a spring, and it's going to be losing pressure as the other object needs more pressure to move faster. It's going to be losing velocity. The spring's losing velocity as the object is gaining velocity. So some percentage of the spring's energy can never get into the object. All right, the velocities of the objects it moves has been measured. So again, you say so, and you say so with what? What kind of precision and to what kind of standards? So I could do the elephant and mouse experiment with this scale. Should that be written up as a paper and published as an absolute proof? Is that your argument? That the shitty, crappy, dirty, filthy experiment should somehow be held up and said, that's good enough evidence? So, I mean, maybe if I just glue some plastic on the end of a tin can and make myself a blurry telescope, I can do the Eddington experiment with my blurry telescope. And speaking of the the Eddington experiment, that's part of the reason why Pyrrho is such a despicable character. He actually worked in the industry that analyzes all that data from satellite images and does the telemetry and all that kind of stuff. And so, he knows what the Eddington experiment is. He knows how difficult it is to measure these tiny little bits that you're trying to measure. He probably also knows that it has nothing to do with objects behind the sun. It has to do with objects outside the sun's corona. And that it's a critical experiment in the sense that it's a bold claim to say that light is bent twice as much by gravity. So they haven't repeated the experiment outside the margin of error since the original experiment. The original experiment, I don't think Pyrrho is going to say that didn't happen, but there was at a time on the internet where you could find stuff, and you could actually find Eddington's journal published. And right in his own journal, he says, I was expecting 10,000 stars per glass slide, and I only got 1,000. A 10% of the data. 90% degrade in the data. An amazingly horrible outcome. All right, and he clearly states, I wouldn't stake my life on these results. And yet the results got a New York Times headline saying Einstein proven right. Now, you think that's good science? Can you honestly tell me that's the way science should work? That a really shitty experiment done way outside the margins of credibility should be credible enough to say somebody was proven right by it. I think that anybody who says that's good science, you're the science denier. You're the enemy of science if you think science shouldn't be more credible than that. And then in the 100 years since, never repeated. They didn't even try it when there was a perfect 12 noon eclipse over North America. They didn't even try the experiment. There's no talk of anyone ever doing it from space or even attempting it from space when there's 400 times better resolution. You don't even need a telescope. You just need a decent camera. And you could probably do it from Jupiter because you have so much better resolution. So if I would have told, Einstein even brought up Jupiter, as a possible candidate. And he just pointed out, yeah, well, it's 100 times less visible. But if you have 400 times better resolution, 100 times less visible is no problem because you still have 300 times better resolution. So isn't that sort of the joke? It's 100 times less visible, but from space, it's 400 times more visible. So you only lost 100. So you're still 300 times ahead of Eddington. 300 times better seeing. And you can use Jupiter, which doesn't have any corona. It's not on fire. None of that crap is going to get in your way. And they still haven't tried it. Nothing. Physics has done nothing on the subject at all. And you're going to tell me I'm the science denier or I'm the science insulter? No, you're clearly insulting intelligence, insulting my intelligence by saying I should be convinced by this crappy evidence. Again, you haven't even dropped 4 pounds 1 foot and 1 pound 4 feet and proven that it's the same amount of energy. You haven't even done that experiment. Haven't dropped them in a swimming pool. Haven't dropped them to anything to measure how much momentum they create through their motion. You've done nothing. All right. The momentum from the spring depends on the mass of the spring is pushing. So this is more bullshit. It has a certain amount of MV, and it can give it back as slow motion or fast motion. So that's just sort of bullshit. It has a certain amount of momentum to give, and there's not any advantage or disadvantage beyond the fact that the spring doesn't have an unlimited velocity. So if you go really light, the spring can't give it any energy at all because the spring can't move as fast as it needs to move to give it a high enough velocity. So you can't launch bullets with springs because you can't make the metal of the spring move quick enough. It is not the same for two objects of different mass. So again, it's always the same momentum, so that's just a lie. It stores a certain amount of energy, and if you can use a lever, as Brozo proved. So again, you're just denying the Brozo experiment. So I'll just bring it up again, just to rub it in everybody's face. All right, but Brozo did the experiment. All right, so here's the spring. I'm going to compress the spring exactly the same amount. Okay, I'm going to push on it. Okay, compress it. All right, now here's my lever. I'm going to compress the spring, and then I'm going to put a 2 mass here, and I'm going to put a 1 mass here. All right, You can see that, right? Yeah, just make sure. Yeah, you can see that. I have a crooked lever, but whatever. All right, so you do the experiment. Same compression. You pull the lever back the same amount, so the lever moves exactly the same in the two circumstances. Same compression, same exact speed. Okay, and it launches this at 1 velocity, and it launches this at almost 2. I mean, the real results are 19 and 11. Okay, pretty close anyway. All right, and the idea was, he skid them across glass, which was a good idea to get rid of as much angular shit as possible, but he's still measuring the velocity over this entire distance, which is part of the problem, right? Because obviously the slower object loses momentum quicker than the faster object, blah, 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 blah. So yeah, still imperfections, but the fact is it's pretty close to the ideal. I mean, 10, 20. Okay, it's pretty close to 10, 20. Anyway, so what's your argument? The momentum is in the spring. The momentum was delivered to the two objects pretty consistently. So why haven't you dissected this experiment, explained why it's a piece of shit compared to these silly metal-wheeled carts crap and, matchbox cars glued with, pretzels glued on them? I mean, all the other crap experiments have been done. So why don't you explain how you think the theory is different? And again, I did it on my own porch. So again, you're just kind of denying what I've seen for myself. All right, is I hung a lever, okay, to create a balance. I hung it from the top. All right, same amount of lever on both sides. Clearly just put, the 4 mass here. All right, and the 1 mass 4 units of distance out here. I get 4 times the velocity here that I get here. All right, and it oscillates, 100 times, just fine. Now, obviously, the only energy it's moving from side to side is the energy of the lever. So a little hunk of this lever moves from this side, and then it moves to this side, and it moves to this side. So that's the only piece of energy that's causing the motion. But clearly, the motion, the energy, is swinging from this side going up against gravity, and then it swings to this side up against gravity. And clearly, that motion is always converted into exactly the same momentum. The momentum here is exactly the same as the momentum on this side. Your theory says this is 4x the energy, and yet it's a perfect oscillator. How can 4x the energy be on this side that's on this side? Not possible, not reasonable. You don't have any answer, you don't have any response. You just do this crap, where you change the subject and talk shit. All right, the momentum from the spring depends on the mass. Okay, it is not the same for the two objects of different mass. So how easy it is to transfer energy is a whole different subject than what energy does it have. And my argument is in the Newton's cradle, it doesn't matter, clearly, in terms of transferring between equal masses. So I can make these twice as big or 3 times as big or 4 times as big, and it'll still work quite well. All right, so nothing gets broken, okay, by mass, by itself. But if I was to change the mass of one of these balls, okay, and now I'm doing a conversion between different masses, I'm not going to get an oscillator anymore. I'm going to get an uneven oscillation, all right, and the energy is going to be dissipated quicker because of that unevenness in the oscillation. So there's always a hard time converting energy from a light thing into a heavy thing, or from a heavy thing into a light thing. Heavy things moving slowly can't give much momentum to an object when it hits it, because it can only give the velocity it has. So a thing going 30 miles an hour can't push something 300 miles an hour. Now you can put a spring in front of it and help it a little bit, and so maybe you can get up from 30 to 40, but you're still not going to be able to get it to 100 if it's 1/3 the mass or something. So you still have limitations into how you can convert energy from different massed objects, because they need a different amount of time to absorb energy. Heavy things need more time to absorb energy. Light things don't need much time at all to absorb the energy. These are the facts. Okay. The ability of energy to move objects depends on mass. The lighter object is easier to push, so it's just not a fact. Okay, they're both the same ability to absorb energy. One of them just needs more time. Okay, but there's no other impediment besides providing enough time for it to absorb the energy. That's why pulleys work. That's why levers work, because they change the amount of time. All right, and therefore easier to get the energy into. It has equal energy, so he says he's using the word energy to mean kinetic energy. So again, this is just such a theft of vocabulary. Obviously, I'm arguing that momentum is energy. Okay, so and that's what it was. Quantity of motion is what the word energy means now, and quantity of motion 300 years ago was momentum. Anyway, equal energy to a higher momentum object. So let's see. Let's read it again. It has equal energy to a higher momentum object. So I don't even know what that means. It doesn't have equal kinetic energy. All right, the big object is big and slow, the hard to put energy into. So, the Brozosians argue exactly the opposite. They argue it's really easy to push a 16-pound bowling ball, and it's really hard to push an 8-pound bowling ball. So if I were to pick up a 8-pound ball, I can't expect to be able to throw it twice as fast. Their argument is I can only throw it 0.4 faster. So if I threw the 16-pound ball at 8 miles an hour, they're saying I can only throw the 8-pound ball 10 miles an hour. I can't throw it 16 miles an hour. I can only throw it 0.4 faster, which is obviously a nonsense. So again, it's all these axioms, all these statements by you people. You don't have any experimental evidence, and you certainly don't have any credible scientific evidence. You don't have great scientific evidence. You don't have a volume of evidence. You have scant, almost non-existent evidence. And here you are so arrogantly saying you've proven it. It's all settled. We don't need you. We don't need to have this conversation. And it's not settled at all. You've just all said, yes, I believe Jesus walked on water. Yes, I believe the burning bush was actually on fire. Yes, I think God wrote on rocks. Yes, you're just saying that, yes, all of these little axioms you're going to accept, and you don't have to see any evidence or any proof or anything because you just want to believe it. And that's all it is. It's just a religion. And you're the ones attacking the scientific method, in that you're the ones saying, I don't need evidence. I don't need proof. I don't need credible evidence. I don't need good reasoning. I can accept lots of contradictions, and that's just fine. You're the enemies of science. All right, because science is supposed to be exactly the opposite. Okay, details, tons of evidence. That's what science wants. All right, and clearly if there's an inconsistency, it should bother you. If two experiments are saying two opposite things about the reality, you should pursue an answer. So if you're making free momentum or you're destroying kinetic energy, you should be able to recognize that there's something wrong with your frickin' theory. All right. So anyway, shorter than the first version by 10 minutes or so. So that's good. Yeah, so I don't think, there's the simple little gravity arguments I guess is missing from here. But you just can't deny some of this stuff, and it's just, they're sitting there and overtly denying the obvious truth. Okay, so, pyrrho, do you actually believe that you can't slide across thin ice by changing how much pressure you're putting on the ice? That is, you can successfully traverse thin ice by basically eliminating your weight, okay, by reducing how much you weigh, how much pressure you'll be putting on the surface, how much contact you'll be making with it, by sliding across it quickly, basically proving it's a time-dependent force. And the same argument is with the gravity. Do you really think if I'm going from point A to point B in space, and I'm in a gravitational field, that it doesn't matter how fast I move from point A to point B? That it's always the same amount of gravity no matter how fast I travel. I think it's just such an obvious fact that now it's completely time dependent. Time decides it all. Time decides how far you get to fall. And how far you fall or how far you move doesn't tell you, okay, as cleanly. So time is the real cause. Distance is the effect. And that's, I don't see, again, how a reasonable person cannot understand that that's the absolute truth. Time is the cause. Distance is the effect. And yes, sometimes the distance and the cause and the effect are the same. But obviously, if I give something an initial velocity, okay, in gravity, I give it an initial velocity towards the Earth, it's going to be in the gravity a lot less time, and it's not going to gain any energy. Because it won't be in the gravity long enough to gain any energy. Fact. And if I do the opposite and I move through gravity very slowly, I'll do a lot more work. If I lift 100 pounds really, really slowly, I'll do a lot more work than if I lift it as quickly as possible. Just an absolute fact. And these people saying they're defenders of science say I am invalid and wrong and misguided and foolish and even evil because I would challenge that silly statement by them that I must believe, okay, what they claim to be true. MGH is true. Work equals force times distance. It's true. I have to believe it. All the facts indicate. When no facts indicate, no experiments really indicate. And if you really analyze the evidence, you can see there isn't any. Simple truth. They haven't done the simplest experiments. None of them. They haven't dropped 4 pounds 1 foot and 1 pound 4 feet and measured the energy. They haven't done the experiment. With all their physics men and all their physics horses and all that kind of crap, they haven't tried to put that little Humpty Dumpty piece of evidence on the table. They haven't done anything. Experiment again, from space, the Eddington experiment cost $50. They haven't done it. Don't need an eclipse. Tiny amount is 5 minutes of satellite time. No eclipse, 5 minutes of satellite time. Done. They haven't done it. Haven't tried it. We're supposed to believe they haven't even tried it. Amazing bullshit. Especially when you think that Google routinely takes photographs of everybody's backyard. I mean, you can go on the internet and you can see almost every square foot of the Earth now in pretty high resolution. And you're telling me they don't have 5 minutes of that camera's time to just look at the edge of Jupiter and see if they can see a star moving funny? Come on. It's not a realistic assertion. It's ludicrous to believe. It's impossible to believe that you have faith and confidence in a physics that hasn't done such a simple experiment that was so profoundly important. I mean, it's the foundation of so much of your physics. Again, if Einstein wasn't made credible, mv squared might not have been as credible. I mean, the fact is they're still, they're measuring the mass of an electron with mv squared. They're measuring the energy of, noble gas, gases, and they're measuring the energy of all kinds of things using the kinetic energy formula. They're obviously getting wrong answers, and all those wrong answers are piling up and creating the fact that the reason why they can't do anything with this physics is because the numbers are wrong. Because they say an electron is so much lighter than it actually is, their measurement of our electrons and protons, the mass of our electrons and protons, it doesn't equal our actual physical mass. When theoretically it has to equal our mass. That's what we're made out of. The electrons and protons are what's being pushed by gravity. They're the ones collecting the force. They're the ones collecting the momentum. They have to equal our mass. So they haven't got anything right. And these arrogant, flat-headed, belligerently obnoxious, fair trial deniers, fair fight deniers, distract and side subject bullshitters think they're defending the truth and doing something honorable when they're clearly doing something very dishonorable, when they insult my intelligence and your intelligence by claiming science is being done well, when clearly it's being done like a religion. They're just telling you what's true. They're not showing it to be true. They're not proving it to be true. They're not even bothering to collect any evidence to bring to trial. They think they can just get away with, if it don't fit, you got to quit. That they think that's all they need is slogans and jargon and pretty pictures. They just keep showing you little flashy, sparky things, and that's all they have to do, because you're all just chasing glitter and bullshit. You know, why don't they just, they're probably going to publish someday a picture of a cloud's actual silver lining, like the black hole picture. They'll manufacture some sort of bizarre picture of the silver lining. As that's how corrupt the physics is. It's all just a wooey fable, propagandized by these phantasmagorical, silly people trying to, rewrite the story of material existence in the universe. They don't like the true story, and so they have bears wearing hats and smoking cigars because they don't like the real story. Fact.